Hi everyone. Today we're going to talk about the system design of key value data store. So when you think about the design of the key value, there are actually two completely different designs that you can implement key value data store. The first one is optimized for availability, and this is the Cassandra use case or RugsDB, LevelDB, etc. And the second one is a database optimized for consistency, which would have a completely different design with consensus algorithms, masters and followers, and relaxed consistency. We'll talk about it in the next video, and today we're going to focus on the availability key value data store. In this video, we're going to go deeper into the design. We're going to talk about the data structures in memory and the file system. We'll talk about the read and write paths. And in the end, we'll review our design and prove that it does not support consistency. With that, let's get in the design of the key value data store optimized for availability. Let's first define the requirements. We want to design a key value database that is highly available. We also want to make sure that replication level is adjustable by the client. We want to make sure the database is performant and provides high throughput, both writes and reads. So with these requirements, let's first think about it high level. If you want to write a lot of data very fast, then we need to make sure that our replication is asynchronous and we store some sort of data in the memory. Because if we want to write a lot of data, we can't just be storing every single write to the file system. It's just not going to be fast enough. So in our design, we would want to have a memory component where we would store the most recent writes done in the system. We would want to have a storage that would store all the writes and manage all the database data. And we need some tool to make sure that in case our server fails or crashes, we do not lose the state that we keep in the memory. Now, as we have these three main components, let's look at the workflow. As you can see on the diagram, we would have a memory component called mentable, where it would store the most recent writes to the database. Then the memory would be flashed to the file system in the form of SStable, and then we would have a commit log. This is a state of our mentable, so every single write that gets to our database and stored in memory would be also stored in the commit log on the file system. Now let's look deeper. As the database receives a write, it does two things. First, it stores it in the mentable, and it also stores it in the commit log. This way, we guarantee that the data will not be lost. Even in the server crashes, the data will remain in the commit log, and on the server start again, the commit log would be replayed into memory again and flashed to the file system as a data, so we'll not lose any data. The commit log would be represented as a write-ahead log that would consist of multiple segments that would store the data from the memtable. The moment the memtable is flashed to the file system, we would rotate the commit log and create a new one where new data would be stored. So for every single mentable, we would have a separate file in the commit log. Now the mentable, how would we maintain the data there? And what we would want to do is first sort our data. If we have a sort data, it's going to be easier for us to read it from the file system. And in our case, we'll be using the LSM tree design. So the data in the memtable would be sorted. As you're receiving a data, we would just maintain a data structure that would be either a B tree or a skip list, and make sure that the data is sorted in memory. Once the time comes to flash the data to SStable, we would take the sorted data by the key and dump it into the SStable. SStable stands for sorted string table, that pretty much consists of keys and values in the same file sorted by the keys. Every single SStable can have a multiple indices that we would also want to write to optimize the read later on. Making a sorted tree in memory also helps us to handle duplicate messages or updates that come into the database, because we can just mutate the state in memory very fast, and then as it gets stored to the file system, we guarantee that all the data in the memtable is unique. All the keys are unique. Now let's see, every single time we flash the system, we create a new file. So we'll have a lot of files. What do we do with them? We would want to do some sort of compaction. There are at least two ways we can compact the SStables. The first one is size-based, which means it's based on the size of SStable. Every single time we flash data on the disk, we create a new file, and then let's say there are 4 files. We get them all, load them in the memory, and merge them into single file. By doing so, we perform multiple things. First, we reduce the number of files. Secondly, we can still have duplicative messages across multiple SStables. So when they nourish multiple SStables, we also making sure that all the keys are unique and in sorted order. As you can see on this diagram, we can have multiple levels of SStables. The first one is level 0. These are all the files created by flashing binary state to the file system. So these files might contain duplicates or overlapping keys. Then, starting from L2 and further, all the SStables would not contain any overlapping or duplicate keys. As we are compacting the SStables, we would also take care of all the updates, tombstones, and removes that were done on our data. Now we have a lot of SStables of different levels and different sizes. How do we search for a specific key? The data is ordered, so for every single SStable, either when it's created or when they are merged, there is going to be an index file created. And an index file would maintain a mapping between a data key and an offset of where the record is stored in SStable. So as you can see on the diagram, this would be the format. They would have a key value in our SStables, and then the index file would maintain a partial mapping between keys and offsets. We wouldn't have every single key in the index. We can just index, let's say, every kilobyte of data. So if you want to find a specific key, since it's ordered, first we use an index to find a approximate position, and then we can just iterate through the 1 kilobyte of data to find a specific record we are looking for. Now, how are we going to perform reads? The most naive approach to implement a read would be just to go to our file system, look through every single index file on the file system to see whether it contains the key, and if it does, then use that index to find the closest position to that key in the SStable. And as we know, that closest position, just do the iterative scan through the 1 kilobyte of data and find the value for the specific key. But there are a lot of improvements that we can put on top of it. The first one is we need to find a file. Instead of going through all the files, all the indices to understand where the data is located, we can just use Bloom filter and optimize it. But it will tell us is the files where the data is definitely not located. So now we reduce amount of files to scan. Number 2, we can use a key cache. We can cache some of our indices in memory, and as the request comes in, we first check the cache, whether we know exactly where the file is located, and go straight into the SS file table instead of going through the file index stored on the file system. Number 3, we can use a file system page cache, which is additional way we can optimize the reads and avoid checking too many files to the file system, as well as loading those files into memory. Now, as we've covered the read and write path, let's see how we can make our database available. By now, we can write and read from database, but it's still a single node. So to make it highly available, we would need to first implement replication, and second, run multiple servers of our database. So let's assume that we want to add more servers. The way we would do it is just by giving those servers a seed IP of the server that is already running. Then new servers would just join, discover the server that is already running, and read information about the cluster and metadata from that server. If we use this approach, we need to make sure that every single server has access to information about all other nodes and all other tables and partitions. To do that, we need to make sure that system data, which is an information about the cluster, about the nodes, ranges, tables, and partitions, is replicated across all the servers. And this is why we should talk about the tables and partitioning. So our database would support, let's say, key spaces. In every single key space, we would be able to create multiple tables, and every single table would be partitioned across multiple servers. And every partition would represent a specific range on the consistent hashing ring. Now, as we create a table, it gets partitioned, partitions assigned to specific servers, and nodes information about the nodes and namespaces, tables, and partitions stored in the system key space that is replicated across all the nodes. This way, no matter what node goes down, we still aware of the state and every node acts as a master. Now how about the replication? In our case, since it's peer-to-peer communication between nodes, every node can act as a master and can replicate data to other nodes. What we want to do is to have a flexible read and write replication. So every single time we write the data, the producer should be able to specify on how many servers the data has to be replicated and how many servers need to acknowledge data before returning success back to the client. So let's look at the example. When we have our producer client, first, the client has to understand and know about the state of the cluster, what servers, partitions, tables we have. So the first thing our producer would do is make a call to any IPs in our cluster, because every IP can act as a master, and retrieve information about the nodes, tables, and partitions. This way, when we write data, we can compute the hash of our key and send the data to one of the servers that own that specific partition for this record. This way, the server that owns the partition would receive the record, write it locally, and then, based on the write consistency, replicate this data synchronously across a specified number of nodes. This way, we can support the write consistency as well as different replication effect. With the read request, it would work in a very similar way. When the client sent a read request to our server, that request would go to the server that owns the partition where the data is. So the server would act as a coordinator and first look at the local database, local file storage to find that key. And then if clients requested to a quorum read, the coordinator would send the request to more servers and read the same key out of those servers. Then all those keys would come back. The most recent version of the key would be chosen and returned back to the client. And if there is a discrepancy on the coordinator from the values that we receive from other servers, we would do what's called a read repair. Right? We would get the most recent valued version and then update the servers that have stale data. This is how we would remediate the data inconsistency in our system. So with this approach, the most efficient way to provide availability, high throughput, and read consistency would be to do quorum writes and quorum reads, which means that we would want to have a quorum of node acknowledge the write, and then as we read the data, a quorum of node to read the data and then choose the most recent version of the data before returning it back to the client. Now let's see if this design supports any consistency. First, let's define what consistency is. Consistency means that every client that reads data from the database receives the same result. No matter whether the server goes down or something else happens in the system, as the data reads always consistent. If there is a value 1, that every single client receives the value 1. But does our system support this type of consistency? In theory, if we think about it, if we do the quorum writes and quorum reads, then at least a quorum of nodes would be able to receive the most recent version of the write and then return it back to the client. But in reality, this is not true. For instance, if you look at the diagram here, you can see the panel writer that would want to do a quorum write on the 3 replicates. After the first write is done, reader A sends the request to the database, and 1 gets 2 values, 1 value out of replica 2 and 1 value out of replica 3. It retrieves the most recent version, which is x equals 1, and returns 1 back to the client. Later on, let's say our writes are delayed for some reason, and another reader B reads the data from our database in the same quorum read consistency. And we might hit 2 nodes that don't have the updated data yet, and we would receive value 0 for X. This is what it means for a database to be inconsistent. We had 2 reads and they returned different results. So even if we have a quorum replication and quorum reads and writes, the database still does not support consistency and might return different results for different clients that query database in different type. What it means is that we achieved the availability, but completely failed the consistency. In the next video, I'm going to talk about how to design a highly consistent key-value data store and optimize for consistency over the availability. If you found this video useful, then sure, I can subscribe, and I'll see you in the next one.